Good morning everyone, and welcome to today's worked exam answer video, which I know is the first one for quite a long time, but I'm really hoping that I will be able to get back into the swing of these as we approach the exams this summer. So as per my video a few weeks ago, a couple of people replied on Instagram with topics that they wanted me to cover, and one of those topics was buffer calculations. So that's where I'm choosing to start today. So we have a 5-mark buffer question here, which reads as follows. We've been given the Ka for butanoic acid. We've then been told that we're going to add 20 centimetres cubed of a 0.1 mole per decimetre cubed sodium hydroxide solution to 25 centimetres cubed of a 0.1 mole per decimetre cubed butanoic acid solution, and we've been asked to calculate the pH of the solution formed. Now, this is an AQA question, and I am surprised that they haven't done this, because historically they always have, but it's really important for us to see that they may not do this in the future. They haven't used the word buffer once in this question. And historically, if it was a buffer calculation, they would say calculate the pH of the buffer solution formed. Now, how do I therefore know that this is a buffer solution? Well, initially, it may not be obvious to look at from the information, but once we've worked out the number of moles of the sodium hydroxide and the number of moles of the butanoic acid solution, we will see that the weak acid is in excess, meaning that all the alkali is going to have reacted away, and when the weak acid and the alkali react, they produce the salt. And a buffer is when we have a weak acid and the salt of the weak acid in solution together. And those conditions are going to be met here, as we will see. So that is how I then know it is a buffer calculation. So I'm going to highlight some information in the question, as I always do, and I've got different colours. I've got green for my salt, I've got purple for my alkali, and I've got orange for my weak acid. I'm going to write a balanced chemical equation. I'm going to work out the moles of the alkali and the weak acid, and then I'll come back to you. So there you can see I've got my balanced chemical equation between the butanoic acid and the sodium hydroxide, which is going to make sodium butanoate, which is the salt, and water, and that equation is already balanced. And I've then copied down from the question the concentration of the weak acid and the alkali. The volumes I've converted from centimetres cubed into decimetres cubed, and that's enabled me to work out the moles of each by doing concentration times volume. So at this point, we can see that we've got more moles of the weak acid than we do the alkali, meaning that the weak acid is in excess and all the alkali is going to react. When they react together, they're going to make our salt. So we are going to be left with a solution that only contains weak acid, salt, and water. And that means that we have got a buffer solution. Had we have done this with a strong acid and an alkali, we wouldn't have generated a buffer solution, because to be a buffer solution, we have to have a weak acid and the salt of the weak acid. If the alkali had been in excess, again, we would not have had a buffer solution, because the alkali would then remain and there would be no weak acid. So again, that wouldn't constitute a buffer. So next thing I need to do is work out how many moles of butanoic acid are left over after it reacts with the alkali, work out how many moles of salt are made, then I can write my Ka expression, rearrange it to get H plus equals. Why do I want to get H plus equals? Because that's what's going to enable me to get pH. So I'll do a couple more steps and then I'll come back. Okie dokie, so because the alkali is the limiting reagent, all the alkali will be used up, leaving me with none. And because these react in a 1-to-1 ratio, that tells me that I will lose the same amount of weak acid. So I can then work out that if I had initially 0.00250 moles of the weak acid, and I've reacted away 0.00200 moles, that I will be left with 0.00050 moles of my weak acid. In terms of how much salt is produced, the salt is also in a 1-to-1 ratio with the weak acid and the alkali. So if I am reacting away 0.00200 moles of sodium hydroxide, I am going to be making 0.00200 moles of my salt. The next thing I've done is I've written my Ka expression. So it is the products of the dissociation of my weak acid divided by the weak acid itself. We've got square brackets here for concentrations, and this CH3, CH2, CH2, CO- is going to be the salt, and the CH3, CH2, CH2, COOH is my weak acid, just to be clear on that. Some people might write a generic Ka expression and use A- and HA. I would strongly advise against that when you know what the specific names of the weak acid, the alkali and the salt are. Then you can see that I've rearranged my Ka expression to get H plus equals. So I've times up by the weak acid and then I've divided through by the salt. Now you'll also notice that I've dropped my square brackets for the weak acid and the salt. That is because, and I think this is a much easier way of working with buffer solutions, we can use the moles of the weak acid and the salt here. Now, this only works for buffer solutions, so please do not try and attempt to do this in any other acids and bases calculation. But the reason why we can use the moles here is because if concentration is worked out by doing moles divided by volume, and we were to do moles divided by volume of the weak acid divided by moles over volume for the salt, the volumes on the bottom will cancel, and thus calculating the concentrations is a completely unnecessary step. If you wanted to work out the concentrations, you could, but you're then going to have to take these moles and divide it by the new total volume, which would be the volume of the acid and the alkali added together, and you're going to end up with exactly the same answer. So my advice would be always to use the moles at this point. But if you are going to use the moles here, it's really important you don't add the square brackets because square brackets denote concentration. So I've now got my value for Ka from the question. I've got my moles of the weak acid. I've got my moles of the salt. So at this point, I'm subbing my 3 numbers in to work out my H plus and get my pH, which I'll do for you now. And there we have it. I have calculated the value for the concentration of H plus ions by doing the value for Ka from the top of the question times by the moles of the weak acid divided by the moles of the salt. That has given me a H plus concentration of 3.775 times 10 to the minus 6 moles per decimeter cubed, and to work out pH we always do minus log base 10 of the H plus concentration. So that's what I typed into my calculator, and that gives me 5.42 for the pH, which we should always give to 2 decimal places. If anybody has any questions, as always, please do either drop me a comment or drop me a message. I will do some more buffer calculation questions as well as lots of other different topics in this series. So again, if you've got any recommendations of what you would like me to cover, again, please just let me know. Hope you all have a really lovely day. Thanks, guys.